Welcome back to the Lowdown on Physics. This is screencast 9.2 in a series on VCE Unit 3 Physics, studying motion in 1 and 2 dimensions. Today we're looking at aspects of horizontal uniform circular motion. In the previous screencast we were looking at horizontal uniform circular motion, and that's the same today. The only difference is we now have no flat surface that the object is resting on. So what that means is we've got two forces acting. We've got tension acting up the string, and we've got to account now for the weight force. We don't have that cancelled out by a normal reaction force. So breaking tension up into its vector components allows us to analyse the circular motion. Here the vertical component of the tension must equal the weight force. If it does not, the object will either move up or move down. The horizontal component of the tension provides the circular motion. Okay, so the centripetal force provided by that tension is the horizontal component that will cause it to move around the object. We have an angle theta here, and that's the angle to the horizontal that the object's moving at. And using that we can come up with some relationships between tension, centripetal force and the weight force. So T sine theta, that's the opposite over the hypotenuse. T sine theta must equal the weight force. T cos theta is equal to the centripetal force, which is mv squared on r, or ma. So let's work through a couple of examples relating to this. We have a ball given a mass. We're given a mass in grams, so be careful of your units. There's the first trick in this question. It's given on a cord, 1 metre length, swings at an angle of 60 degrees to the vertical. Second trick in this question. So giving ourselves a diagram and labelling it, that means our horizontal angle must be 30 degrees. First part is to determine the radius of the ball's path, that is this length in here. Now to do that we can look at that in terms of sine of 60 equals the opposite, the radius, over the hypotenuse. Okay, obviously the diagram's not to scale, but solving that we get r over 1, or r equals sine 60, which is 0.866 metres. Identify all the forces on the ball. We'll bring our diagram back up. We've got two key forces, weight force down and tension up. Of course we're going to break this one up into components, but when it asks for you in your exam to identify the forces, there are those two forces and that is it. What is the tension in the rope? Well, let's have a look at the relationship between weight and tension. We've got T sine 30, not the 60, is equal to the weight force. So substituting in and solving, we get tension equal to 3 newtons. So what's the net force acting on the ball then? The net force is the one that's causing acceleration, and so that is your horizontal component, or your centripetal force. So we've got mv squared on r, and that's the same as T cos theta. So we've got 3 times cos 60, which is equal to 2.6 newtons. Note that is a rounded off approximation. I won't use that when I use the value in my next question. How fast is the ball travelling? Okay, so F net equals mv squared on r. We can rearrange that. So multiply by r, divide by m, take the square root. We substitute in. There's the actual value in the calculator. Again, not a rounded value, actual value from the calculator, divided by our mass in kilograms, and we have 3.87 metres per second. Okay, let's consider now, instead of a car moving on a flat surface, what happens when it's on a banked curve? Okay, you see this on corners where they put a slight little bank in it so that the cars go around it a bit easier. What's the purpose of that? And basically it's because this normal reaction force can be broken up into vector components. You've got the weight force down, but then it also provides you with some centripetal force. So again, net force, vertical components are cancelled out by weight, otherwise the car's either going off the road up into the air or it's falling through the road, and therefore the net force must be that force that's pushing it round the corner. If If we look at this, we've got a triangle here. We know the adjacent side, we know the opposite side. That's because this angle here is the same as this little one in here. That's perpendicular, so that's 90 minus the angle, which makes, if that's 90 minus that, that means that is the same angle at the top as we see at the horizontal. So that relationship is opposite over adjacent, centripetal force over gravitational force equals tan theta. So let's look at that in a question. We've got a cyclist, mass in kilograms, radius in meters, and we've got a bank of 40 degrees to the horizontal. So all the units are in the correct form. So we've got F net equals FC, which is equal to mg tan theta. Where did that come from? Well, tan theta was FC over weight, or FC over mg, multiplied by mg. We've got FC equals tan theta. So substitute in, we've got 10 times 70 times tan 40, we have 587.37 newtons. That's the entire centripetal force that's applied. If the question asked the average force per tyre, 2 tyres, you'd have to divide by 2. Okay, second question. What speed would be required so that there was 0 frictional force up or down the bank? That is, so that the cyclist wouldn't be tempted to move up or down, or be pushed up or down by going either too fast or too slow. At the exact right speed, the cyclist would just move around the bank at the same level. So in order to calculate that, we know the centripetal force that's required. Therefore, that's equal to mv squared over r. Rearranging again for v, multiply by r, divide by m, take the square root. Substituting in our net force that we calculated last question, we get 22.44 meters per second. At that value, the cyclist would not have to steer and apply additional frictional forces and would just move around the bank at the same height. That's it for now. I'll see you in class shortly and we'll go through some more of these type questions.